All right, good morning, folks. Only one full week of class left after today, plus a residual lecture on the Monday, December 8th, but we're pretty quickly getting down to the bottom of the term here. Since the last time I brought this up, the response rate has more than doubled, which is fantastic. I'd love to see this get to 50%, but I know that a lot of people won't hear me talk about this until they watch the video, if they do, and so I'm pretty sure everybody here has filled out the survey, and whether or not I'll be able to convince any more people through them watching the videos is up to them mostly. But please, if you haven't already filled out the survey, please go ahead and do so. We are done talking about flexural members, and I would say we are done talking about flexural members in the context of the joists and girders in our example buildings and your project buildings. We're going to focus one more time on this expression today. You know that for sections that have very thick web flanges and they're fully laterally braced or there's no lateral torsional buckling concerns, we can take the moment resistance as the full plastic moment capacity, which is phi ZFY. And we're going to focus on how we can use that expression today to design a certain detail that's going to help us support the columns at the base of the foundation, because today we're going to be talking about column base plates. Basically, we have a really strong column that's carrying a load down to the foundation. If we put the column straight on top of the concrete, I know you haven't taken concrete materials class yet, but concrete's like 30 MPa in terms of a compressive resistance. Compare that to steel, which is 300 and something, depending on what kind of steel you're using. Just put this I shape straight down on the concrete foundation, you're going to crush your concrete. And so to prevent that, we spread that load out using a great big thick plate at the bottom of our column. And that plate at the bottom also helps us install the columns. I talked about that a little bit in lecture 3 earlier this term. Right, so we've got a really strong steel column, usually, well, I guess 350, 345, whatever, MPa yield strength. We're trying to take that down to a concrete strength, and at most, it's probably 35 MPa for most typical concrete foundations. It's probably anywhere from 24 to 35 MPa and maybe even 34 MPa. In any case, you'd specify what concrete strength you want. But we need something with a great big area to distribute the load in the column out over a larger area so that we can satisfy the bearing strength of the concrete foundation, prevent concrete crushing. And if we carry the load even further down, if you're thinking about the foundations class you're taking with Dr. Nasser right now, you've talked about bearing capacity, and so as we go down from a strong steel structure to a weaker concrete pedestal down to the soil base that we're trying to transfer the load down to, the material gets weaker and weaker, and so we need more and more bearing area to prevent failing those materials. So this is the footing that would transfer the load. We're going to talk about the footing as much in this class. Well, we're not going to talk about it at all. But you can think of this base plate almost as if it's the footing for the steel column down to the concrete pedestal. Okay, so we're trying to increase that area as we go down to prevent failing the weaker materials that we're trying to transfer the loads down to. Basically, again, here we're looking at steel strength and concrete strength, and we want to make sure that the base plate dimensions, and we're going to call them B for the base plate width, that's aligned with the flange of our columns, and C, which is the base plate width aligned with the depth of the columns. We need to make sure that B times C provides enough area, right? Because basically we've got some stress on this little I shape, and we need to spread that out over a square or rectangular area to satisfy the concrete bearing resistance limit states. There are a bunch of different ways we can consider base plates. Sometimes they'll carry really heavy loads. And so this would be a W310 by, I think, 200 and something, or maybe even 300 and something, a very heavy column, carrying significant compression forces down to the foundation, so we need a really, really big base. And in those situations, normally they're big enough, we can stick the anchors in the corners of the base plate, and that helps them level the base plate in the field, and I'll show you what that looks like in a minute. Sometimes base plates may be relatively lightly loaded, so if the column is a little bit lighter, it's not carrying as much compression force, the base plate area doesn't need to prevent concrete crushing. And in those instances, we usually try and place the anchor rods within the footprint of the wide flange section to avoid having to make it bigger than we need to make it. These are real details from the drawings from the Justice Building. So the photo at the start on the backdrop of the slide, that's of this base plate. And then there are columns that are on the foundation frost wall along King Street, and their base plates look something like the little detail that's shown on the left there. Basically, after today, you should be able to discuss the purpose of column base plates in terms of the structural design and the column erection. You should be able to determine minimum required bearing area and the size the plan dimensions for heavily loaded base plates for ultimate limit states, and calculate the required thickness for the base plate for both ultimate and serviceability limit states. Okay, so we're going to understand why we need a base plate. We're going to figure out how big it needs to be and how thick it needs to be based on a few different considerations. Does anyone have any questions about any of these three items before we continue on with the rest of the material for the morning? I think Pull Everywhere is going to, oh no, good. I feel like I'm finally winning with Pull Everywhere here. So I just want to get a quick sense. Again, usually when I ask these questions at the start of the lecture, I haven't taught you anything yet, so I don't expect you to know any answers. But for these columns that we're trying to install and transfer load to, I've talked a bit about the base plate. We're going to figure out how big the base plate needs to be, and we tend to throw anchor rods in there. And really, they're just gravity columns. They're just carrying a vertical load. What are the anchor rods for? Maybe they're very important for the compression resistance of the base plate. Maybe it's not really they're important, they're just a matter of good detailing. Maybe they're very important for the construction of the building, and maybe you're not really sure what they're for. Maybe another 10 seconds here or so for those who want to participate. All right, good enough. So yeah, they're pretty important for the construction of the structure. There's not a whole lot, if any, lateral load acting on those anchor rods and gravity columns. They're really just supporting the floors upward. The wind loads might get transferred to brace frames, and so sometimes the anchor rods need to carry shear, but for simple columns, they're really just there to help during the construction of the steel structure. CSA S16 doesn't tell us a whole lot about how we should be designing base plates or anchor rods, or at least it didn't tell us very much up until the more recent standard published in 2024, but we're not talking about that yet in this course. Basically, we need to make sure that suitable provision is made to transfer factored axial loads, including uplift, shears, and moments to footings and foundations, and forces present during construction and in the finished structure need to be resisted. Okay, so for our simple base plates, we're just talking about axial loads, and really we're just talking about compression today. Unless the base plate is at the bottom of a column of a braced frame and it needs to transfer some shear, or it's at the bottom of a column in a moment frame we haven't talked about at all in this course and it needs to transfer moment. They're typically just the simple columns. Most columns in our building just carry compression, and so in terms of loads, that's all we're really going to be considering. To consider forces present during construction as well as the finished structure. So a column, that's just supporting loads in the finished structure. It's just carrying the floors above it. There's nothing else it's doing. But during construction, we do have a column. It's something like this. It's on the foundation, and we've installed some anchor rods at the base, maybe something like that. And we, from time to time, need to make sure that it's capable of resisting, some nominal wind load or something like that. We're not really going to get into construction loads in this class. We're going to focus on the finished structure, the base plate design that tends to be more important. In terms of the design of the anchor rods, though, during construction, the anchor rods are there to make sure that the column can resist some nominal amount of moment at the bottom as well as some nominal amount of shear from whatever wind loads might be present during the construction of the building. That's what we mean by during construction. We're going to focus, though, on loads that are present in the finished structure. We have some provisions for minimum amount of anchor rods. Columns have to have at least 4. And if we have 4 non-collinear anchor rods, it's not feasible for safety, then we need special precautions. And basically what we're talking about there is, here we've got 4 collinear anchor rods, it means none of the anchor rods other than two, these would be collinear, and then those ones would be like 2, 3, 4 that are in a row. Basically, those would be 4 collinear anchor rods. We want to have 4 anchor rods that are spaced relatively far apart from each other, usually in a square rectangle, because when they're installing these things, they need to have these 4 points to make sure that the column doesn't tumble down. And so if you just had, for example, a column with 2 anchor rods, then basically the column can tumble that way because there's nothing to prevent uplift at the other side. We always need to have 4 for safety reasons during construction. Otherwise, we need some other kind of special bracing arrangement, and that's up to the contractor to figure out how to handle the engineer's responsibility so much. The only thing it really tells us about resistance is about the concrete. Okay, so compressive resistance of concrete shall be determined in accordance with clause 10.8 of another standard. Okay, so in reinforced concrete design next term, you're going to talk a lot about CSA A23.3. We're not focusing on that standard in this, how to calculate the compressive resistance of the concrete under the base plate. And so when compression exists over the entire base plate, that the bearing resistance is distributed uniformly over the area of the base plate, and that's going to be important for us in terms of determining what the stresses in the base plate might be when we start to get to the concrete limit states. So this is what a typical column base plate arrangement might look like. We'll see on the other underside here, we have the anchor rod, right? So the anchor rod is already present after the concrete work is done. And then on the anchor rod is going to be what's called the leveling nut. So that's a leveling nut. And usually there'd be a washer there as well. So the leveling nut and washer will be present. The column's going to get installed. They're going to put the holes of the base plate onto the leveling nuts. And then they're going to come and put the washer on top to kind of secure the column in place. And the leveling nut is something that they can use. They'll have a surveyor on site. They'll be evaluating the plumbness of the column, and so they can spin the nuts under the 4 corners until the column is level. And then they can tighten and torque the top nut so that the column is in place and secure. And then once that's there, we don't really want to leave the anchor rods to carry all the gravity loads. And so once the leveling nuts are in place and everything is torqued together, they're going to inject what's called a high-strength, non-shrink grout underneath the base plate, something like this. And so they're basically filling it with a cementitious material to eventually take that compression force down to the top of the foundation. Okay, so the nuts are there, and leveling nuts just provide some nominal stability during construction. They're not responsible for carrying the vertical force under the actual gravity loads in the finished condition. That's the responsibility of the grout that they inject under the base plate once they finish installing the column. Okay? So the last thing I'll talk about before I take questions, basically, is the grout's going to distribute that load down to the foundation. We need the grout is strong, and normally we just say grout shall be high strength, low shrink material that's stronger than the concrete foundation or something like that. And if we go to CSA 23.3 to figure out how strong the concrete's going to be in compression, B stands for bearing. BR is bearing resistance. We take 85% of phi C, which is a resistance factor for concrete, times F prime, 28-day compressive strength of concrete, which you'll learn about in concrete materials class. Are you in concrete materials now or next term? Did anyone take concrete materials yet? Next term must be. And then we've got A1, which is the bearing area. So for the most part in class, bearing area is just going to be B times C, or the overall base plate area. Okay, so basically, to summarize quickly, we need to make sure that there's sufficient area of our base plate. Basically, we're going to have a rectangular square base plate where that area is going to be B times C. We need to make sure we have at least 4 anchor rods so that we can install the column in place, make sure it's plumb, and then we inject the gap underneath the base plate and the top of the foundation with a high to distribute the load over the pedestal area. Then we make sure that the total load on that column or on that base plate doesn't exceed the bearing resistance, and we basically need to make sure that A1 is big enough so that the bearing resistance is bigger than whatever compression is acting on that column. Does anyone have any questions about those concepts before we continue on? Okay, so I will write here quickly, bearing resistance needs to exceed whatever the factored compression force is on the column that we're designing the base plate for. That force that we calculated from the structural analysis needs to get down to the foundation and ultimately down to the soil. And so the question is, what does A1 need to be? In our case here, this is actually a pretty simple inverse problem. We know that CF needs to be, I don't know why I have it like that, greater than, oh no, sorry, that's right. CF needs to be less than 0.85 VC F prime C A1. And so we can simply rearrange that equation to figure out how much area we need, right? So we know that the bearing area of needs to exceed whatever the force is divided by the stress we're allowed to, the upper limit on the stress that we're allowed to take for the concrete and bearing, which is 0.85 VC F prime C. And again here, just a quick reminder, VC is 0.65, and F prime C is that 28-day compressive strength, which usually ranges from something like 20 to 35 MPa, roughly. And we know that the bearing area of the base plate, well, that's for the engineer to determine. We need to specify B and C so that the bearing area is big enough to satisfy the equation just above that. Right? So we can calculate the A1 required and then figure out how big B and C need to be. So that's fine. Basically, we have one equation to figure out A, but then we have two unknowns, right? B and C. If we have one equation and two unknowns, that kind of makes our life a little bit difficult. What should we do to figure out what B and C should be so that we can figure out how to provide this total area A1 so we're not crushing the concrete? What should we do with B and C to figure out what these dimensions should be based on the single value of A1 that we back calculated to satisfy the bearing resistance strength of the concrete? What can we do with B and C? Ideas? What's the easiest thing that you can think of? Make them equal, right? You just make a square. That's the easiest thing. And all of a sudden we have an equation. We can say, let's make B equal to C. That's convenient because usually these W shapes for columns are square, but the width and depth are similar enough that the outer bounds of the wide flange section are roughly square. Simply make a square base plate. That's the easiest thing that we could do. The other thing that we might consider, okay, we could say, well, C should be proportional to D, and maybe B could be proportional to B. But that's kind of annoying because it always changes. And the other thing that makes that annoying is if you make B 410 millimeters and you make C 400 millimeters, the anchor rods are already there on site. And if they weld the base plate on the wrong way, 90 degrees off of each other, all of a sudden you have a field fit-up issue. You have to send the column back to site or grind everything off and do field welding, which is not the best case scenario. B equals C is simple, but it's also practical because there won't be any, or there should be less risk of having field fit-up issues. They're going to weld it on. It doesn't matter if it's 90 degrees or 180 degrees. It's always going to fit the same. And as long as you make the holes for the anchor rods in the same place in all the corners, then you are mitigating the risk of field fit-up issues. Okay, so that's the easiest thing to do. The other thing that you could do if it was really necessary, okay, I really want to make sure that I have enough room so that I can fit anchor rods in the corners. Maybe it's a tall column and I want to make sure they have enough leverage relative to the center of the base plate. The further the anchor rods are from the center of the more stable the column is when they're trying to install it in the field. So from a safety perspective, you might say, okay, I'm going to want to make sure that the anchor rods will fit in the corners, so I'm just going to make sure the base plate overall is enough so that I can fit everything in that way. When you're detailing anchor rods, you want to make sure millimeter gap between the edge of the plate and the center of the hole directions. And the minimum edge distance is usually something like 30 millimeters. And so the minimum size for the base plate, if you want to plumb, you would say, okay, big B would be plus 160. Big C would be the depth also plus 160. But you could make it square again. You could just say, okay, well, if C is bigger than B, then I'll make B equal to C again, and we can figure out what A1 is based on B times C. Okay, so we have to make sure that it's big enough, that we're not crushing the concrete, but sometimes you also want to make sure that it will be big enough to make sure that you can fit the anchor rods in the corners for to improve the safety of during the installation process in the field. Okay, so are there any questions about what options are available to us in terms of figuring out what B and C should be before we continue on? Okay, I'm going to skip the next slide because I don't remember why it's there and I don't think it's particularly important. When we start figuring out what thickness the base plate needs to be, the first of the engineers to figure out what B and C should be, we have some ways to figure out what B and C should be. When we're looking at the contact area, we're going to basically be distributing CF out over the area of the base plate, right? So the bearing stress, I'm just going to call it Q because I don't have any other better way to call it. The bearing stress under the base plate is going to be CF over B times C. Form stress under the area, and that contact stress is CF over BC. And so we're going to assume that that area is uniform. And now all of a sudden you might be able to identify here that we have a uniform pressure over a plate that's extending beyond the boundaries of the bottom of the column. And basically what that's going to do is it's going to force the base plate to bend up. And now all of a sudden we have a flexion. Right? We've got some overhangs here that we're going to try to make sure the moment resistance at the edge of the overhang or at the root of the cantilever is greater than the applied moment coming from the uniform pressure applied to the base plate. I'll show you what this looks like. If we have a uniform pressure applied over the area of the base plate, basically what's going to happen is the plate is either going to bend one of two ways. It's hard to tell at first. You can see here all of this red is yielding of the base plate. It's really clear from the bottom here. You can see there's a pretty clear straight through the red here and here where we're developing a significant amount of yielding, and that yielding is happening up around what we call a yield line. And so we might say that the yield line is something like this, and we basically need to figure out or determine what an appropriate distance to that yield line is going to be, because what we have essentially is a uniform pressure underneath this area, something like this. It's applying load up to the cantilever, and what we're going to do is we're going to treat this base plate as if it is a cantilever beam, and we're going to assume that the support of that cantilever beam is at the location of wherever that hinge line may be developing. So how do we calculate the moment resistance of something like this? I'll show you in a minute how to get the moment acting on the edge, but how would we figure out how strong this plate would be in bending along a line that looks something like this? Any ideas? Well, basically, if we look at the cross-section at the root of the overhang here, what we just have is the width of our base plate, right? And so in this case, that dimension here is C, and whatever thickness we have for that base plate is going to be T. So we have a cross-section that's basically just a long rectangle, okay? And our goal here is to figure out what the moment resistance is of a rectangular shape. To do that, we can come and look at the typical dimensions of a rectangle. Let's just say it doesn't really matter what B and C are here, or B and D. But we can apply the same idea of having a plastic stress distribution above and below the neutral axis. And because this is a solid cross-section, there are no concerns for local buckling. So no local buckling concerns. And there also aren't going to be any lateral torsional buckling concerns, because when we're looking at this base plate, it's bending about the weak axis, and the natural state of lateral torsional buckling is the beam wants to try and flip on its side to bend about the weak axis. So there are going to be no lateral torsional buckling concerns either. Okay, so no lateral torsional buckling concerns. So really, we're just trying to figure out what the plastic moment capacity of this rectangle is, and we want to make sure that that capacity exceeds whatever moment's acting on that base plate. So if we do the same thing here, basically we have an area right above the neutral axis. Jesus. The area of that rectangle is equal to b times d over 2. The distance to the center of that is d over 4. And we have that on the bottom as well. So the force above the neutral axis is bd over 2 Fy. The distance to that force is d over 4. And we also down here have bd over 2 Fy. And the distance down to there is d over 4. If we take the moment couple, the distance between those is d over 2. And we'll remember that the moment that's acting on the section is equal to whatever one of the forces is multiplied by the distance between them. We have a moment couple where the forces are equal and opposite at a distance of d over 2. So we're going to take the force, which is bd over 2 times Fy, multiply that by d over 2, and we're going to get the moment resistance is bd squared over 4 times Fy. Okay? So we know we can take the plastic moment resistance because, well, there's no local buckling considerations that we need to worry about. And it's just a wide plate bending about its axis, so there are no lateral torsional buckling concerns either. This BD squared over 4, if we separate all the stuff out from the yield strength, that's the plastic section modulus for a rectangle. Okay, so here it's shown quite clearly. We've got BD squared over 4. That is Z shape. And if we were to put this in the context of our base plate section, our base plate is basically just one long rectangle. In our case, if we're bending about the tips of the flanges, we're calling this big C, and we're calling this T. And so Z in our particular case here is going to be C times T squared over 4. Okay, and so we can calculate the moment resistance of our base plate by taking that Z value, multiplying it by Fy, and including our resistance factor to make sure we're following the limit states design philosophy. Does anyone have any questions about how we might go about calculating the moment resistance of the base plate through the section where it's bending the most? Okay. So how do we apply this then? Well, what we're going to do is we have to look and determine where the base plate is going to be developing this maximum moment. The way we typically treat this is we look at two possible ways. Either the base plate is going to bend about these two hinge lines, something like what I showed here in the video. If I can play it again. I have to play them separately, I guess. So we could assume that the plate's going to bend basically about a line that passes through the cross-section somewhere here. And basically, if you were to try to observe where the base plate would bend, the location of those yield lines relative to the center of the section is about 0.4 times the flange width away. And so we assume that hinge line passes somewhere here, 0.8b. And if the hinge line is here, we're going to work with a cantilevered bit of plate that has an overhang length equal to n. It's also possible, though, that we might develop hinge lines in the other direction if the other overhang happens to be larger. And so we might have yield lines that look something like this. Those are located at 0.95d apart, and so 0.025d from the tips of the flanges. And so if we know where those locations are, then we can figure out what the overall moment is on that cross-section. I'm going to work with this one here. Okay, so we're going to look at this yield line where we're yielding about 0.8b. And we're going to call that overhang distance n. Okay, so we've got a cantilever beam, and it's got an overhang distance n. It's also loaded, maybe I'll draw this the other way around. We've got n up here. We've got a pressure under the base of the plate, something like this. All right, so we have a uniform load. And if we were to look at that in the direction here, basically the linear load present is going to be equal to the pressure. Remember, the pressure under the plate is CF over B times C. Well, if we multiply that by the distance C, then we're going to get the uniform load acting on the beam, right, or the equivalent cantilever, right? This is basically the tributary width for base plate that we're looking at is equal to C. And we can turn that pressure into a line load acting on this base plate, which is CF over B. Okay, so we've got a pressure bending the plate up. We've got an internal moment coming from that pressure bending the plate upwards. And we're going to call that the factored moment acting on that yield line. MF, the factored moment, is going to be equal to CF B. That's the line load. That's going to get multiplied by, in our case here, N to get the equivalent point load, multiplied by N over 2, which is the location of that resultant force. And so we end up with CF over B times over 2. Okay, so we have a factored moment acting on the base plate, F over 2B times N squared. And we want to make sure that this is less than or equal to the moment resistance. The moment resistance is phi Z, which is, in our case here, for our width of plate, CT squared over 4 times Fy. And so we can basically set CF over B to be N squared has to be less than or equal to CT squared over 4 Fy. We want T, right? That's what we're trying to figure out right now, is how thick does this base plate need to be so that it's strong enough in bending? Is there anything else here that we don't know already at this point? Should we probably know what CF is if we're designing the base plate for the column? If we've already picked the column, we're trying to fit a base plate to the column. If we've already picked the column, we know what CF is. We should have figured that out already from the structural analysis and the load factoring. We should already know what B and C are, right? So they show up here. We've got B and C. Fy, because we'll just specify for plate steel 350 megapascals, usually 350 W for typical plate steel. And so all we need to do is reverse this to figure out what T should be. Right, so if we do that, we get that the minimum plate thickness, I'm just using EP, is going to be equal to 2 times CF. And the way that I set up the problem there, it was times N squared over BC times phi Fy. But M might be a longer overhang. Decides it based on that overhang. Basically, if we know what the base plate size is, we can calculate N or M. We take the larger of the values, plug it into this equation along with the base plate dimension C, the yield strength Fy, and our compressive resistance CF, and we can figure out how thick that base plate needs to be so that it has a sufficient bending moment resistance. Does anybody have any questions about any of those ideas or where this equation come from before we go ahead and see some other things and how we can apply these things to design a base plate for our column? All right. So the other thing we need to do is we need to make sure that the base plate's actually thick enough to develop the uniform pressure that we're assuming is present under the base plate. This is an assumption. We're assuming here that this is a uniform pressure equal to CF over BC. So we need to make sure that the base plate is actually stiff enough in order to develop the uniform pressure. So I've got a fresh tissue, don't worry here. If I have a point load and I put my finger on the tissue, do you think that this tissue is doing a good job at distributing the point load from my finger over the table? No, it's really thin, right? It's really flexible, so the pressure on the table is just going to be the same as whatever I'm applying to the tissue, right? But if I was to stack up, I don't know, 3 books or a great big thick piece of steel, then the thicker that plate is, the more it's able to distribute that pressure over the table area. Thankfully, concrete's relatively, to steel, though it is getting loaded directly in axial loading. So we have a minimum thickness that we need to consider on our so that this uniform pressure assumption becomes. And the rule that we need to follow for the most part is we want to make sure that the minimum plate thickness is at least to whatever the biggest overhang is divided by 5. And that's just a rule of thumb. I have no idea where it comes from, but I know that if we do that, the idea behind using this minimum thickness is to make sure that the plate is not deflecting too much so that we're developing the uniform pressure that we're assuming for design. Are there any questions about that last step before we get into how this applies in design and to go through an example of how to size a base plate for our example building. So basically what we need to do here, we have to figure out what A1 needs to be, concrete strength for foundations, or we talk to whatever engineer has designed the foundations, figure out what they're specifying. We've calculated CF already from our structural analysis and load factoring, so we calculate A1 to make sure we're not crushing the concrete. We've got some options here. This is another one that I didn't really talk about, but we could try to make it equal so that there's no one governing overhang. That would result in the most efficient use of the material, but it's hard and it's not as practical. The base plate dimensions end up being similar, but you can have things go wrong. The simplest thing to do, where B is equal to C, they can't install it wrong, or at least it's very hard to install a square base plate in the wrong orientation. It could be off by 1 or 2 degrees in terms of how it aligns with the column, but you're not going to have it the wrong. And you can check to make sure that we have enough if you want to make sure that the anchor rods go in the corners. If you don't care where the anchor rods go and you can shove them in the footprint of the base of the W section at all. So we're going to focus on this for now. B is equal to C. Let's make a square base plate. That's one option we can decide. That's a reason. The other thing, once we know what B and C are going to be, we figure out what they should be based on A1, and figure out what TP needs to be for strength. That's to make sure that we can get the full moment resistance MP, and for serviceability, and to make sure that our design assumption makes sense in terms of the uniform pressure developing under the base plate. Okay, so we calculate it as 2CF times N or M squared divided by phi times BCFY. Take the square root. That's for strength. We also calculate M or N over 5. That's for the design assumption. And we size the base plate for the thickest of those two. And again, we'll remember here that in the marketplace, most steel fabricators are rolling plate to the nearest eighth of an inch. And so we're not going to pick 10 millimeters or 20 millimeters. We're going to figure out whatever the thickness should be in millimeters. We're going to figure out what the closest thing is in terms of eighths of an inch. And then we're going to specify whatever the inch thickness is for the base plate. If you have other questions that aren't eye-shaped, these are just some other things. If you're figuring out what N or M are for a rectangular or a square HSS, you can look at that picture. If you want to figure out what it should be for round HSS, you can look at that picture. Are there any questions about this design process before we apply it in an example? Okay, so back to our example building. We previously, in lecture 26, picked a column because we calculated in lecture 5, lecture 6, snow, live, and dead loads on the in lecture 10, we factored that to get CF was 2357, or you did in the Poll Everywhere question. And in lecture 26, we picked a column that was going to work for that particular member in the building. Okay, so we picked a W310 by 97 to be the column in that building. It was the lightest one that would work out of the other options. Of 2357 kilonewtons. We're going to F prime C is 28 MPa, and we're going to design a column base plate to transfer that load from the column down to that foundation with that 28-day compressive strength. Okay. Are there any questions about what we're trying to accomplish in the example before we get into the calculations? Okay. We need to figure out what the minimum area should be. We have F prime C, phi C is 0.65. We have CF, but we need to convert that to newtons to get millimeters squared from MPa. And so the first thing we need to do is figure out what A1 should be equal to. Okay, so A1 should be at least equal to CF over 0.85 phi C F prime C. We take the 2357, we'll convert it to newtons using 10 to the 3, so that when we calculate A1 using newtons and megapascals, we get an area in millimeters squared. We have 0.85 times 0.65 times 28 MPa. Again, because we have newtons in millimeters, when you do the calculation, you have an area in millimeters squared. And so when you do this calculation, A1, by my estimation, needs to be at least 152,359 millimeters squared. Any questions about that step before we continue? So next, we're going to make B equal to C. That's our square base plate. Okay, that's the easiest thing to do. And I don't care where the anchor rods are going to be. If the plate's not big enough to fit anchor rods at the corner, that's fine. I'll put them in the footprint of the wide flange section. So we'll just size the base plate for strength and see where that leads us as a result. So by doing that, we can say, okay, B is equal to C, and either of those then will be equal to the square root of A1. So B and C will be equal to the square root of 152,359 millimeters squared. And when I do that calculation, I get something like 390 millimeters, roughly. Okay. So from here, we still have to kind of be cognizant of what the people are going to try and build. We can either try and round this to the nearest 50 millimeters, so that at least if they cut it to inches, then it would work based on the metric dimensions in terms of the equivalent metric dimensions. Or we can just use the actual inch value. If I was to figure out what 16 inches was, right, there's 25.4 millimeters in an inch, and so 16 inches is 406.4 millimeters, right? So that's pretty close to what I calculated. What I'm going to do so that the fabricator's happy is I'm going to make the base plate 16 inches by 16 inches so that they just take their measuring tape, make it 16 by 16, and they're not going to think much about the millimeter measurements. The other thing you could do, the other option, you could say, well, surely they can use the 40 centimeter measurement on a tape measure if they've got a tape that has both values. So it depends. If you're doing an imperial project, you would use 16 inches. If you're doing a metric project, you might say it's 400 millimeters. They can cut the plate to whatever they want because they're just going to use a laser cutter to the dimensions that you specify, but you still want to make sure that you're doing something reasonable there. I'm going to go forward with the 16 inches. Okay, let's just assume we're doing a project for Irvings or for MB Power. They tend to still use imperial measurements. Are there any questions about that before we continue on? Okay, so we've got a 16 inch by 16 inch base plate. We have B and C. The next thing we need to figure out is what TP needs to be for strength, right? So B equals C equals 16 inches, which is 406.4 millimeters. Now we need to figure out what TP should be for strength and also for serviceability. We'll check that in a minute. Okay, so we need to calculate TP as the square root of 2CF times N or M squared divided by BC times phi Fy. So before we do that, we need to figure out, okay, if we've got our base plate, it's 406.4 by 406.4, which is 16 inches by 16 inches. And I was to draw my W310 by 97 on top, which might look something like this. Should be using a straight edge, but whatever. So I need to know what B, right? So this is B. And this is D. And I know my hinge lines are at 0.8 B or 0.95 D, right? So for the W310 by 97, we can look that up in the handbook. B is equal to 305 millimeters. D is equal to 308 millimeters. And our goal here is to figure out what N or M should be. So N is this dimension N, and this is M. We need to figure out whether N is going to be bigger than M or the other way around. So we can, did I not write out what N and M should be? I guess I didn't. So if we come back here, we have 0.8B plus 2N is equal to B. So it's pretty easy for us to figure out what's going on here. B is equal to 0.8B plus 2N. So that means that N is going to be equal to B minus 0.8 little b over 2. That's 406. I don't know why I have the decimal beforehand. 406.4 millimeters minus 0.8 times 305 millimeters over 2. And my overhang length n in this case ends up being equal to 81.2 millimeters. And I can do the same thing for m. M was going to be equal to c minus 0.95 d over 2. It should be pretty obvious here. M is not going to be bigger because we're taking away a bigger value from a similar dimension. That's 406.4 minus 0.95 times d, which is 308 millimeters over 2. And we end up with an overhang length m of 56.9 millimeters. Okay, so we have two possible overhang lengths, m or n. N is the bigger of the two. And if we're using that to calculate the minimum base plate thickness, either for strength or for serviceability, this value is going to result in a larger thickness compared to the value of m that we would be using. Any questions about the calculation of those overhang lengths or why we're going to use n here to size our base plate? All right. So now we can do it for strength. Tp, the minimum thickness is going to be equal to the square root of 2 times Cf. In our case here we're using n squared divided by BC phi Fy. Oops. So that for us is equal to the square root. And again, we're going to use newtons, millimeters, and megapascals. 2357 times 10 to the 3 newtons times n, which was 81.2 millimeters squared. BC, they're the same. 406.4 millimeters, 406.4 millimeters, 0.9 for phi. I'm going to use 350W steel, so 350 MPa for Fy. And if I do that calculation, again, which is based on strength, I get 24.4 millimeters. Okay, so to make sure the plate has adequate moment resistance under the uniform pressure under the base plate, based on the larger of the two overhangs, the base plate needs to be at least 24.4 millimeters thick to provide a section that works for moment resistance. Any questions about that calculation or what it means before we do the next check? Okay, so that's for strength, right, ULS. We also need to make sure that there's not an excessive deflection of the base plate so that our pressure is uniform under the base. To do that, we're also going to check that the base plate should be at least greater than n over 5, which is 81.2 millimeters over 5, which is clearly going to be less than what we calculated for strength here, but we'd have 16.2 millimeters, and that's SLS, and really that's to make sure that the design assumption is reasonable so that the thickness we calculate for strength makes sense. Are there any questions about that calculation or what we're doing? Okay, so clearly strength governs here. It's going to give us a thicker plate, 24.4 millimeters, but I'm not going to specify 24.4 millimeters. What equivalent imperial dimension should I specify that's closest to but slightly greater than 24.4 millimeters? That's pretty close to an inch, right, width of your thumb. I'm going to use TP is 1 inch, which is 25.4 millimeters. Okay. So I'm going to specify a 1 inch 16 by 16 square base plate. And so when I'm sketching that on the drawings, I'm basically going to sketch something that looks like this. I didn't really check to see if the base plate anchor rods are going to fit in the corners, but they're not. I'm going to throw them in somewhere there. And I'm going to have a width of 16 inches, a depth of 16 inches, and I'm going to call this a PL 1 inch. That's a 1 inch thick plate. That's 16 by 16. I would locate where the anchor rod specifically should be but that's a detailing exercise that isn't critical to us at the moment. Okay, so from the start, we needed a base plate, and the engineer needs to specify in the drawings B, C, and T. That's the information the fabricator needs. We found B and C to make sure we're not crushing the concrete. We found T to make sure we're not failing the plate in flexure, and we also made sure that the plate was adequately thick so that the design assumption makes sense. We took an equivalent thickness of 1 inch so that you can find it on the marketplace, and they'll cut this to 16 inches by 16 inches in the shop and weld it to the bottom column. Are there any questions about that example before we move to wrap up lecture for the morning? Okay. Well, now you should be able to describe what the base plate's for in terms of structural design and the installation. Determine the minimum bearing area and use that to figure out how the plan dimensions should be sized to make sure we're not crushing the concrete. The required thickness based on the bending strength of the plate, as well as the serviceability requirements to make sure we're not getting excessive deformation. What that's for is to make sure we're developing the uniform stress that we've assumed when we're calculating the base plate thickness for ultimate limit states. Does anyone have any questions about anything that we talked about today before we wrap things up for the weekend? Great. See everybody on Monday. Have a nice weekend. Fill out the student opinion survey over the weekend, please, if you can find time.